So what happens when we have lone pairs? Because there are many molecules that have lone pairs. Well, then we have to distinguish between electron geometry and molecular geometry. And this can seem confusing to students, but it shouldn't be. The electron geometry is looking at the arrangement of the electron groups. We don't care if it's a lone pair or not, just how are the electron groups being arranged. And we just went over all the possible shapes for the electron groups. The molecular geometry only looks at the atoms. So if there's a lone pair, it doesn't have an atom at the end of it, and it's going to make a slightly different shape. If you don't have any lone pairs, the electron and molecular geometries are the same. So the way I think of it is I think about balloons, right? And you arrange the balloons based on your number of electron groups. And then if you have a lone pair, to do the molecular geometry, you say anything with a lone pair, that balloon's invisible. It's there. It's repulsive. But we can't see it. So when we take a picture of the molecule, we only see the visible balloons. So let's look at ammonia. Let's just sketch the Lewis structure over here real quick. There's the Lewis structure for ammonia. We look at the nitrogen and we see there are 1, 2, 3 bonds, single bonds. Those are each electron groups. And there's a lone pair. That is an electron group. So we have 4 electron groups. That's going to form a tetrahedral geometry with the 3 single bonds here bonded to hydrogens and the lone pair up here. That's the electron geometry. It's tetrahedral. To find the molecular geometry, we're going to say, oh, but this doesn't have an atom at the end. We're only taking pictures of the atoms. So this guy's invisible. If he's invisible, and ooh, I can make him invisible. If that guy's invisible, what do we have left? We've got this guy. See that? So that lone pair is there, but molecular geometry is looking at the positions of the atoms in the molecule, not just electrons. Remember, electrons are unbelievably tiny. They are tiny even compared to hydrogen atoms. And so they would not show up on a picture. So this is formed from a tetrahedron, but it's not a tetrahedron. And so this is called a trigonal pyramid. We had trigonal planar, that was flat. If you took this trigonal pyramid and ran over it with a steamroller, it would be flat and be trigonal planar. But it's not a plane. It's not flat. It's three-dimensional. So this center one is bumped up a little bit because of that lone pair. So this is trigonal pyramid. There's different approaches to learning how to identify the shapes of these molecules, and one is to memorize a table, and another is to think about balloons getting away from each other and then making some of them invisible. And I think, at least for me, that works much, much better, to just kind of think about it instead of try to rote memorize some things. So lone pairs usually exert more repulsion than bonding pairs. And this is not it's not a politically correct thing, and it's not, I don't mean this to offend anyone, although I'm sure I'll probably offend someone. So you go to a party, and there's lots of couples, and then there's some single people, right? And I think single people sometimes feel like they're left out, or like people are avoiding them, perhaps. I was single once, too. I didn't really, well, we just won't go there. Anyway, the lone pairs are a little bit like a single person, okay? And so the lone pair is more repulsive, and it pushes these people away. Some people are single for a reason. Others, who knows why. But occasionally you'll run into someone and you're like, well, I can tell why you haven't found anybody. That's the kind of single person we're talking about. We don't, personally know any of those people, but we've met them, like, at Walmart at 3 in the morning. So this lone pair, if it helps you remember that lone pairs are repulsive, the lone pair is more repulsive than these bonds, and so the angles between these single bonds will be slightly smaller, 107, and the angle between the lone pair and the hydrogen atoms will be slightly larger than on a perfect tetrahedron. Okay, so we'll see that. Now, I am not going to get into wanting you to know exactly what that bond angle is, but I do want you to recognize that if there is a lone pair, it's going to push the other atoms a little closer together. So you should be able to tell me that this bond angle is less than 109.5. I don't need you to know how much less, but just that it's less. Okay, so the lone pairs take up a lot of space, and they push the other guys a little bit closer together. So there's multiple possibilities for molecules that have 4 electron groups with lone pairs. Let's look at water, our old friend water. Again, we need a Lewis structure. So the Lewis structure for water is going to look like this. We look at the central atom, oxygen, and we see that it has 1, 2, 3, 4. 4 electron groups. Lone pairs are groups, single bonds are groups. 4 groups. 4 groups arrange themselves in a tetrahedral geometry. So you arrange them like that and you freeze them, and then anything that's a lone pair, you say, oh, that's invisible. Right? It's invisible. It's not going to show up in the picture. So it's like get rid of him and get rid of him, and then what's left? Well, they came up with just this really creative name for that geometry. Bent. It's bent. It's not a line, it's bent. So that's a bent structure. Let me get those lone pairs back. Oops, there we go. So we have 2 lone pairs here. The lone pairs are more repulsive, and so they're going to push these hydrogens together. This hydrogen-oxygen-hydrogen bond angle is going to be less than a perfect 109.5. It's actually 104.5, which is less than for the ammonia, because this one has 2 lone pairs pushing those guys together. Any questions? So, relative repulsion of electron groups. Lone pair repulsion is the greatest. Lone pair with a bonding pair is the next largest, and a bonding pair with a bonding pair is the least amount of relative repulsion. So the number of lone pairs is going to affect our bond angles. This one, methane, has no lone pairs. That's going to be evenly spaced out. The ammonia has 1 bond angle. 1 lone pair. And so these bond angles are a little smaller. That's water. Water has 2 lone pairs, and so this bond angle is even smaller than with the ammonia. So what if we have 5 electron groups with lone pairs? What we did is we went through all the possibilities, 1, 2, 3, 4, 5, 6, 7, and 8. Sorry, we didn't do 7. No, we didn't do 7. Anyway, we went through a bunch of possibilities without lone pairs, and now we're going through them with lone pairs. Sorry, I can't remember what I've been talking about. Okay, let's just draw the Lewis structure for SF4 and see what happens. So SF4, we're going to have, it doesn't, writing with a white marker doesn't work real well. We're going to have a sulfur in the middle and fluorines around the sides. And then how many valence electrons do we have to put in here? Each fluorine has 7, right? So 7 times 4 fluorines is 28. How many valence electrons does sulfur have? 6. So we have 28 plus 6, that's 34. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. What do? We expand the octet. Sulfur's in period 3, it can handle an expanded octet. There's going to be a lone pair on the sulfur, in addition to the 4 bonds. It's violating the octet rule. So when we look at the geometry, we first look at the electron groups. The central atom is sulfur. It has 4 single bonds and 1 lone pair. We look at the Lewis structure so that we know how many electron pairs we're dealing with. The Lewis structure, depending on how we drew it, may or may not have a relationship to the actual shape of the molecule. Often not. 5 groups. 5 groups get away from each other by doing this bipyramidal structure. Now, in the bipyramid, there are 2 different positions. There are the equatorial positions, where the bond angles are 120, and then there's the axial positions, where the bond angles are 90 degrees. The lone pair is more repulsive, so he's going to take a position with larger bond angles. So he's not going to be in an axial position, he's going to be in an equatorial position. So we have the 4 fluorine atoms bonded to the sulfur, and the lone pair is going to be over here. So then that's our electron geometry. It's bipyramidal. It's 2 pyramids. Then we say, well, this guy's invisible. What's left? This is what's left. You're like, yeah, okay, what shape is that? Well, they call it a seesaw. And depending on how creative you are, you may or may not be able to see that. Does that look a little more like a seesaw? Here are the legs, and there's the fulcrum, and then the teeter-totter goes up and down, back and forth like this, right? This one's not actually going to bend, but it'll just rock back and forth. You could make a teeter-totter out of that. So it's called a seesaw. So we've got some of these geometries that have these fancy names, like trigonopyramidal, and then we've got bent and seesaw. If we have 5 electron groups with 2 lone pairs, so here is bromine trifluoride. We look at the central atom, it's got 3 bonds, 2 lone pairs, 5 groups. 5 groups get away from each other in a trigonal bipyramidal shape. So here we've got the up and down, and then we've got the equatorial ones going around the middle. Well, lone pairs are repulsive. They're going to get into those equatorial positions where the bond angles are larger. And then when we make those invisible to look at the molecular geometry, we get this. And that is T-shaped, which, it's a T on its side the way we drew it. There. That looks more like a T. I just took this guy and tipped him over. We can also have 5 electron groups with 3 lone pairs. Xenon difluoride. There's 2 atoms bonded to xenon, so there's 2 single bonds, and then there's 3 lone pairs. Those 3 lone pairs are going to take the spots with the largest bond angles. They're going to take the equatorial positions, and they're going to force the fluorines into the axial positions. So the electron geometry is trigonal bipyramidal, but the molecular geometry is linear. It would be helpful for some of you to get a bag of gumdrops and a package of toothpicks and go home and play with them, okay? And, make the structure with the 5 things getting apart, and then take the gumdrops off of the toothpicks around the middle and eat them, right? It'll be fun. Just be sure to brush your teeth afterwards. But sometimes we just need to play with the things, just some, for kinesthetic learners, this is one of the few times where we can actually manipulate stuff and play with toys. Then we can have 6 electron groups. So 6 electron groups made the octahedral geometry. If we have a lone pair on here, now these are all equivalent positions. All the bond angles are the same, they're 90 degrees. And so that lone pair could be anywhere, it doesn't matter, they're all the same. So the electron geometry is still octahedral, but we make this guy invisible and we're left with this shape. And that's called a square pyramid. Because here's the square, and this is the pyramid part. So it's making a pyramid with a square at the base instead of a triangle. So there's square pyramidal and there's trigonal pyramidal. Xenon hexafluoride, we've got 4 single bonds and 2 lone pairs. So 6 groups gets us the octahedral geometry. Now with the 2 lone pairs, those lone pairs being more repulsive are going to be across from each other. They're going to get far away from each other, and the best that they can do is across. So that will have the others in this equatorial position, and we'll have this square planar geometry. Because this is flat, this is a 2-dimensional flat square. So there's square pyramid and there's square planar. And there's a table from your book that summarizes all these things. And that can be helpful to refer to. But what I recommend doing is first thinking about how many groups, how can they get away from each other. Get these electron geometries straight in your head. We've got linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. The molecular geometries are just variations of those, where you make one or more of those groups invisible. Okay? And if you can think about it that way, then doing problems with this and predicting geometries really is not that hard. If you can't get your mind around that, then it's going to be tough. Any questions? So, summarizing VSPER theory. The geometry of the molecule is determined by the number of electron groups on the central atom. The number of electron groups is determined from the Lewis structure. We have to look at the Lewis structure. What we call electron groups are lone pairs, single bonds, double bonds, triple bonds, or single electrons. You would see single electrons in a free radical. But each of those is one electron group. The geometry is dependent on the repulsions of those groups. Bond angles can vary. We can predict what the ideal bond angle for any of these shapes is, but it's going to vary depending on whether there are lone pairs or not, and because the double and triple bonds are bulkier than the single bonds. So that can affect the bond angles a little bit.